All right, so to finish up chapter 9, we're going to look at some bonding theories. Okay, so bonding happens when wave functions overlap. So we're going to get to that in just a second. But for now, bonding occurs when you have wave functions that overlap in a way that's constructive. Okay, so a simple picture of that. Let's say we have two hydrogen atoms that are going to form a hydrogen-hydrogen single bond. So hydrogen, we have 1s, so we can represent a 1s orbital as a sphere. Okay, so we have a sphere and a sphere. These are supposed to be the same size, but hence sadly, I am a terrible artist. Okay, so if we're gonna have bonding, we need these to overlap in some sort of meaningful or constructive way. So when I've drawn this, I've kind of just overlapped the two spheres. So this sort of wave function or this density overlap here would create a chemical bond. So again, we can look at it as a simple picture like this. We can also look at it when we have, say, something like an s orbital, like for hydrogen, overlapping with a p orbital. Okay, so we can have s and say, for example, chlorine, if we're going to make an HCl bond, S and a P overlapping. So not quite as good as up here. We had much more overlap, but still we get some overlap here to create a chemical bond. So in a sort of simple picture, that is what happens with bonding. Okay, so next, there are two types of bonds that can form. So types of bonds, the first one we have is called a sigma bond. So a sigma bond forms along the axis that connects the two nuclei together. So for example, I made CH4 right here. Okay, so a bond that essentially connects the two atoms, like if you could attach the nuclei of one to the other, that is a sigma bond. So for here, it would be this bond right here, the carbon atom, the hydrogen atom. This is a sigma bond. You can draw a straight line, which is the bond, from the nucleus of one to the other. So along the bonding axis is a sigma bond. So these ones form first, and these are the most common types of bond. Okay, so when we get into higher order bonding, like a double bond or a triple bond, we get the second type. So a pi bond is a bond that forms perpendicular to that bonding axis. Okay, so here we have the example of carbon double bonded to oxygen with a single bond to to hydrogens here. Okay, so what happens between our carbon and our oxygen is you have a single bond that forms first. So again, sigma bond's most common, and these form first. Okay, so what we would have is, for example, say this is my oxygen, and that is my carbon right there. Okay, so what we would have is that single bond forms first. Okay, so carbon, oxygen, that single bond forms first, the sigma bond right there. Okay, so to make that second, so we already have a bond right here. So to form that double bond, we can't pack more electrons here because there's already, 2 electrons in this space. So we're going to go perpendicular. So the way I have it drawn here, and I'm going to kind of draw it a little sort of darker, is remember we have P. Remember our P orbitals are along X, Y, and Z. So this is the Z axis right here where we form our sigma. So let's say this one is along the X axis. Okay, so we formed the sigma bond along Z here. I'll put that there, it's a Z. So now let's say we're going to overlap these bonds up here. And so I don't really have anything, spectacular to show this. I have these here, so say these are those P, so they're going to overlap like this and form the P. So remember there's also a lobe sticking down here. So to form that bond sort of completely, we're going to overlap above and below that axis right there. Okay, so that would be both of these, not forming 1, 2, because again, remember that P has the 2 lobes. Okay, so this is the lobe one of the p lobes overlapping on the top and one on the bottom, just like this. Okay, so this is perpendicular to that bonding axis where those p's would overlap like that. So that's called a pi orbital. Okay, perpendicular, pi, and then along that bonding axis right there, that is the sigma. Okay, so let's take a look at wave functions. So the light there. Okay, so this is in the module. This is bonding theories with some wave functions here. So I'm going to go full screen. Okay, so this is what this one looks like. Bonding theories, atomic wave functions, orbitals combined to form molecular wave functions or molecular orbitals. Okay, so recall that we talked about that electrons, we can describe them as waves. Okay, so waves can interact in two ways. So the first one we have here, these ones are what we call in phase. So we have the up and the down matching exactly with the up and the down. Okay, so when this happens, the up and the up will add together, the down and the down will add together, and you will get sort of a giant wave like you see here. So they combine together. That's called constructive interference. Okay, so what happens if they're not in phase? So let's change color here. What happens if they're not in phase? Do we still have our same wave like this? But what if this wave is out of phase? So if they're out of phase, this sort of down part and this up part cancel each other out. So that would cancel that. And over here, this down part and this up part would cancel each other out. So when we do that, they essentially cancel each other out, and that's called destructive interference. Okay, so that's how waves kind of work. So why is this important? For chemical bonding to occur, we need this situation right here. So to make a bond, we need constructive interference of our waves. So our wave functions need to be in phase. So if two atoms have electron wave functions in phase, they can combine and create a chemical bond. Okay? If they are out of phase, they will not exhibit bonding behavior and will interfere to create what we call an antibonding orbital. So you can think of it exactly what we saw up here, constructive interference or destructive interference. That's the two scenarios that happen when we create bonding. Okay, so as we saw, we have the sigma and we have pi. So when we have along the bonding axis, and when they combine to form constructive interference, we call that sigma. And when they have destructive interference, we call that antibonding, or we call that sigma star. Okay, so sigma represents bonding, sigma star represents antibonding. A couple down, we're going to see pi. So pi would represent constructive or bonding. Pi star would represent destructive or antibonding. Okay, so let's scroll down. Okay, so let's look at 1s. So recall a 1s wave function when we kind of drew it out, look like that. Okay, so all we're doing is just extending it sort of on both sides of the atom. So we always put the nucleus sort of right here at the origin and looked at it. So here, again, we just mirrored it on both sides to say that bonding could occur from either direction. Okay, so if they're in the same phase, like we have here, the hydrogen and the hydrogen, which again, from our diagram below, we represented it with sort of this sort of simple model here. So if the wave functions overlap constructively, we get this here. So we have this region in the middle with increased electron density or increased probability. So we have bonding. Okay, so here again out here where it's starting to go close to zero, the probability, when we create that bond, we get that increased area of probability right here. So this is called a sigma bond, and we show where it came from. So the sigma is what we call a molecular orbital. So we're going to show what atomic orbitals were combined for that. So this one here is called a sigma 1s. It's a sigma bond. It occurred along the bonding axis. So again, remember this. It occurred along. And then the 1s to show where it came from. Okay, so what if we had destructive interference? What if those two hydrogens weren't in phase? So we have one positive and one negative. So if we combine those, look at what we get here. So we combine those, and this is now that region of overlap has a node. So there is no bonding that would occur here. We have destructive interference. So this is called a sigma 1s. We put a star. So that's constructive. That results in bonding. This is destructive. This results in antibonding or no bonding. Or like I said, they cancel each other out with destructive. Okay, so when two atomic orbitals combine, they create two molecular orbitals, a bonding and an antibonding. So it's kind of like a probability thing. So when we combine a 1s with another 1s, they create two. So they would create the sigma, and then they would create a sigma star. So the sigma is lower in energy, and the sigma star is higher in energy. Okay, so however many you have coming in, so we have the atomic orbital of 1s, atomic orbital, and then we have the molecular orbitals of sigma and sigma star. So two atomic orbitals come in to make two molecular orbitals, one with bonding and one with antibonding. Okay, so if we look at what happened here for hydrogen, I'm going to change colors. If we look at what happened for hydrogen, each hydrogen atom has one electron. So hydrogen is 1s1. So this hydrogen atom would have an electron, and this one would have one as well. Okay, so what we do to look at and see if bonding will occur or not is we then put them into orbitals, starting with the lowest and working our way up. So these two atomic orbitals are going to go into bonding orbitals. So these ones here, or molecular orbitals, lowest energy, working our way up. So we would put these electrons right here. So both those electrons would go into this sigma, or this bonding orbital, which would result in creating a bond between the two. So we would expect hydrogen to form a bond with another hydrogen based on this atomic orbital, molecular orbital theory with bonding and antibonding. So that's kind of how this works. Okay, so let's keep moving. We have a fair amount of pages to go through here. So that's our example for 1s. Okay, so it does get a little more complicated. Okay, oh, so here's the picture I just drew you on the other one. So for our hydrogen, 1s, the atomic orbitals forming the molecular orbitals. So again, this one represents constructive. And this one up here is destructive. And so we have constructive, interference, and destructive. So if we get more electrons in constructive, it's going to result in bonding. Okay. So let's look at a P. Let's look at P. All right, so P orbitals, if you recall, they're going to give us a couple scenarios here. So we'll start with sigma, and then we'll move on to pi. So we can get, from P, we can get sigma overlap, and we can get pi. Okay, so Z is along the bonding axis, so here's what we have. So if we are looking at these two here, if we combine them in phase, so orange is the same phase, blue would be the same phase also. So we can combine them in the same phase where, again, yellow was pointing towards yellow, so we get constructive overlap. That's called sigma NPZ. Okay, so for example, if it's 2p, we would call it sigma 2p. Okay, where yellow added in with yellow to create bonding. Okay, so we could look at the wave functions again for that if we wanted to, but it's sort of easier to look at sort of the shapes of the orbitals and how they combine in this way. So this results in bonding. So what if they're out of phase? So if they're out of phase, then we have this section right here canceling out. Okay, so we do not get any constructive overlap here. It results in a node. So we'd expect there to be a node right here where it goes down to 0. And we call this sigma star 2p. Okay, so sigma 2p, sigma star, again, if our nucleus of our atom is right there in the center of those, and this is along the bonding axis there. Okay, so it works the same way. So let's see how it works for pi. Okay, so pi, it gets a little bit weird. So now we have, again, our nucleus in the center. Like we see right here, the bonding axis right here is Z. So now we're above and below. Okay, so remember this thing where I tried to combine them above and below. So that's exactly what we're seeing here. So this one here gives us constructive overlap where the yellow combined with the yellow and the blue combined with the blue. So we call this pi 2p. Okay, so over here, what if we flipped one of these upside down and they were not in phase? So what if I flip this one up? We would get the yellows on the opposite sort of diagonal and the blues diagonal. So that's going to form, again, that node right there. So this is pi 2p with the star. Okay, so then if we flip that around, so I had this way, we can also have above and below, like this, where we combine p's above and we combine them below. Okay, so above and below. So that's what we have here. So if they combine constructively, this is also a pi 2p. And if they combine destructively, again, to give us that node right there, we get pi star 2p. Okay, so from a 2p or any kind of p subshell, we get 1 along the axis and 2 that are going to be pi. So from a 2p atomic, we get 1 sigma molecular orbital, and we get 2 pi molecular orbitals. Okay, so 1 along the bonding axis, which we just saw, and then we get 1 up and down this way, and then we get 1 up and down this way. Okay, so let's take a look at what that kind of looks like. So I have this here. Fix the light. Okay, so I have this here to kind of look at what happens. Okay, so let me get the correct colors. All right, so with 1s, these are my atomic orbitals on this side. So I have 1s and a 1s. So when my atomic orbitals combine to form molecular orbitals, I know I'm going to form a sigma and a sigma star. Okay, so lower in energy is the sigma, so we'll call it sigma 1s. So these combine to form a sigma 1s, but they're also going to form a higher antibonding, sigma 1s star. Okay, so these two atomic orbitals form 2 molecular orbitals, one where we have constructive interference, one where we have destructive interference. Okay, so next, 2s, the same thing. Okay, so 2s can do the same thing. So we can form a sigma, now 2s, and we can form a sigma 2s star. So constructive, and now we have destructive. Okay, so not bad so far. So now up here, I have them with different colors. Okay, so remember we have one that's going to form sigma. So my blue one, we're going to have sigma overlap. And the red one, we're going to have pi overlap. So it depends on which sort of atom we have here. And I'll talk about that in a minute, about which ones are lower in energy. But we'll start with the red. Okay, so these are the two perpendicular. So remember these guys, the perpendicular ones. So that's these, the pi's. So these are a little bit lower in energy. So I'm going to put them right here. So this is pi 2p. Okay, so pi 2p. So they also form 1, 2. They form pi 2p star. Okay, so higher in energy, they form pi 2p star. So quite a big energy gap between those two. Okay, so in the center of those, oh here. So okay, so from those atomic, we get the pi 2p and the pi star 2p. So then from the the 2pz, that again is along the bonding axis, we get the sigma 2p, and we get the sigma star 2p. Okay, so kind of look at what we have here. So 1, 2, 3, 4, 5, 6 atomic orbitals that combine to form 1, 2, 3, 4, 5, 6 molecular orbitals. Okay, so atomic orbitals are here, and then molecular orbitals are in the center. Okay, so this is what that looks like. So it's a very complicated picture. We do have a shorthand for this, but I wanted you to see where this comes from. It comes from constructive, destructive, constructive, destructive. There's orbitals combine constructively and destructively all the way through. Okay, so we'll come back to this. Let's go back now and show you the shorthand for what we just did. Oops, undo here. All right, so it's a little bit easier to represent it this way with just some boxes. So I've essentially just eliminated the I've just eliminated the atomic orbitals that I used on the side to build these. So I'm just looking at the molecular orbitals. So kind of remember what I had. Again, those going through the center. So 1, 2, 3, 4. 1, 2, 1, 1, 1, 2. So 1, 1, 2, 3, 4. 1, 2, 1, 1, 2, 1. Okay. Oh, I did one of those backwards. Okay, my bad. All right, so let's go through now and look. So this figure here we have is used. So you see there's a slight difference. So this one we have the 2p a little bit lower. The pi 2p is lower than the sigma 2p. Over here, those are flipped. The sigma 2p is lower in energy than the pi 2p. So for this figure over here, this is the energy order for B2, C2, and N2, or any heterogeneous mixture of those, like a carbon boron diatomic or something like that, or a nitrogen carbon. The one over here we use for O2, F2, neon, and any, heteronuclear combination of those, like a OF or something like that. Okay, and so the way it works is exactly how we did atomic orbitals, where you put electrons in, starting at the bottom and working your way up. So let's do an example. Okay, then we're going to calculate the bonding order in just a second. Okay, so let's look. Oops, sorry about that. Okay, so we're going to do F2 plus. Okay, so F2 plus. Okay, so we're going to use this one right here. So we're going to, here, let's change color. So we have F2 plus. Okay, so let's look at how many total electrons we have for fluorine. So from my period, so we're starting all the way down at the 1s. So we're going to look at total electrons. So for fluorine, that's 9. Okay, so let's look at what we have. We get 9 from each fluorine, which gives us 18. Because this is F2+, we're going to take one away. So we have 17 electrons to put in. So we're going to do exactly what we did previous. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, separately for first. 13, 14, 15, 16, and 17. Okay, so we have them separate in degenerate orbitals before we fill them. So this is where the electrons would be in these molecular orbitals for F2+. Okay, so we can approximate the bonding order for this. So bonding order equals 1/2 bonding electrons, subtract antibonding electrons. Okay, so let's do some colors here. So let's use blue. Okay, so we'll make blue the bonding electrons. Okay, so these are bonding, these are bonding, these are bonding. Okay, and then these here are also bonding. Okay, I know those are bonding because they don't have the stars. I know that bondings are just the plain. They have the stars on them. Those are the antibonding. So let's count what we have. 2, 4, 6, 8, 10. Okay, so we have 1/2 times 10 minus. Okay, so let's go, I don't know, how about orange? Okay, so our antibonding will circle in orange. So these with the stars, these ones are antibonding. And then these ones here. Okay, so we have 2, 4, 6, 7. So we have 1/2 times 10 minus 7. So 10 minus 7 is 3. 10 minus 7 is 3. So this leaves us 3 over 2, which tells us 1 and 1/2. So we have a bond order of 1 and 1/2. Okay, so we can end up with halves, just like we saw when we had resonance structures. Our bond orders could be like 1 1/2 or 1 1/3 or something like that. So this tells us if we had F2+, we could expect something about like a 1 1/2 bond order. And that's because we have an unpaired lone electron here that would be forming that sort of half bond. Okay, so this is pretty good at predicting the bond order here, just simply, again, by tracking your bonding and non-bonding electrons. Okay, so let's do another one. We have this other side here that's sort of doesn't have anything on it, so might as well use it. So we need some sort of combination of carbon and nitrogen. How about a cyanide? Let's go Cn minus. Okay, let's look at the bond order for Cn minus. Okay, so carbon is 6, nitrogen is 7. So we get 6 plus 7 plus 1, which gives us 14. So we have 14 total electrons for Cn minus. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so we have a different scenario here. All of our electrons are paired up in this one. Okay, so let's go back to our colors. Oh no, I use this color. Okay, so we have bonding, bonding. All of this is bonding. And then we have antibonding here and here. Okay, so let's look at our bond order. So we have 2, 4, 6, 8, 10. This is going to be 1/2 of 10 minus. Here we have 1, 2, 3, 4, and minus 4. Okay, so 10 minus 4 is 6. Half of 6 is 3. So we would expect this bond order for cyanide to be 3. So we would expect to have a triple bond between carbon and nitrogen in cyanide based off of how the electrons are filled into this diagram. Again, so take a look. We have lots and lots of electrons in these bonding orbitals. And only a few electrons that were in those destructive. Or with F2 plus, we had a few extra electrons in those destructive orbitals there, which resulted in having less bonding between the two. Okay, so what happens if we have equal numbers of bonding and antibonding filled up? Well, if they're equal, we kind of take a look at our formula here. If these two terms are the same, we end up with 0. So essentially all your electrons in your bonding orbitals would cancel all of those in your antibonding orbitals, and your overall result would be that you have no bonding. Okay, so that's how this works. This works for, we're only going to see examples of this with diatomics, and it will only be in the second row. So when you have to do this on, say, an exam, or when you do these in the packets and things like that, it will only be in that second row. So boron, carbon, nitrogen, oxygen, fluorine, and neon. All you need to do is remember which one of these two you have to use. And again, the only difference is here, that this one is here in this diagram and this one is here in this one. Everything else about it is identical. Okay, so again, just note which one you used for which to fill in the proper diagram. Okay, so this is our first part of bonding. We will have one additional lecture to talk about these things called hybrid orbitals. But for now, that is this for the first section of bonding.